there should be a search bar. Okay, there should be a search bar that opens up. And then in here, I can search for whatever command I'm looking for. In this case, I just want to create a new project. So by searching up create new project, it will take you to this new page, which looks exactly like what you saw in my slideshow. And here's what we'll set up, where we'll set up the new project and give it all the information it needs to create the correct template. So in here, it says select a project type, either example or template. So going over here, we'll do template. And because we're in the Java programming language, we'll click Java. And then it'll ask us which template we're using. I'm sure that some teams have already experimented with the time-based, which is a great place to start, but we'll be moving towards command-based. So I'll just click command-based. And then all that is set up. And then here it's asking me to pick my base folder. So whatever folder you use for your FRC stuff, you can just create a project there. Here I just have a folder specific for FRC coding, and then I'll give it a name. I'll just call it FRC demo code. You can name it whatever you need to name it for your robot or whatever the competition is. And then the last field here is just your team number, and I'll put in my team number. And this last option here is asking to enable desktop support. By default, it isn't marked, but I would recommend that you do it, because as you do go forward with more advanced things, there are certain features you need, which are only accessible if you do select this. So I'm just going to select this while I'm starting out here, and then you should be good to generate your project. So it's saying project successfully created. Would you like to open the folder? So yes, I'll open in a new folder. So in a new window, and one sec. My apologies. So yeah, it should be opened up. I believe it is right here. One sec. Right here. So yeah, right now it's completely empty. There's nothing on it, and we'll learn how to add stuff to it. But I'm just going to jump back to my presentation. Okay, so we've successfully created a new project, but there's just some things I'll go over, which is why we chose Java and what your other options are. So FRC is compatible with a couple of different options, but most teams will use Java. And this session will go over the basics of FRC Java coding, and it's also the most commonly used language. So right now there's 4 major options that you can choose from. The first, and the one I'm most comfortable with, is Java. There's lots of pros to it. The pros include, like, it's very easy and it's very beginner friendly. So it's perfect for a new team that's just starting out and doesn't have any experience yet. It's also the most popular option out there, which comes with lots of documentations and lots of examples. So it's really easy to get help from other people. There's also a lot of YouTube tutorials. And let's say you're at a competition and you're stuck with something, chances are there will be other teams that can help you because you are using Java. The only slight disadvantages that come with Java is that it tends to be a little bit slower than other languages you can use. I personally haven't noticed that, and it's worked perfectly fine, and it really isn't much of a concern. The second most popular option is C++, and the pros that come with this are that it's faster, it's also more customizable, and it's a really good option if your programmers already have some experience in C++. But if you're a new team, the biggest downside is that the learning curve is just a lot steeper. It's something that you have to spend more time learning, and you need a lot more practice. It's also not as common, so you might not find a team that's also using C++. Based on a statistic I read a while back, I think anywhere between 60 to 70% of teams use Java. So you're probably better off using that if you still need the support from other teams. So your third option is LabVIEW. And the pros with this is that it's quite different because it's more graphical and it's visual coding rather than text-based. So it's somewhere in between text-based and drag and drop coding. So it's good if you don't want to do all that typing. But on the downsides, there's not as much support and it's not as widely used, which means that there's not as much documentation available and just less people in the community that can help you if you do get stuck. The last option is Python. It's not official with FRC yet, but it's really easy to learn. And the good thing is that it's growing really fast. There are many teams that are experimenting with Python. So I wouldn't be surprised if, let's say 2 to 3 years from now, it does become a major official language of FRC. The only downsides right now is that there isn't much documentation available and there are fewer resources because it's not official. But other than that, it's not a bad option. But for now, I'd definitely stick with Java if you are just starting out with coding. So the question is, why command-based, right? Because if your robot is working perfectly fine in your time-based system, then why should you change? So this was a situation I was in a little while back as well, because in my first ever competition, our entire robot was time-based, and then I only transitioned between that first and second competition. And in my experience, this transition really improved our robot and made it a lot more effective. It also made it a lot easier for me to maintain the code and add stuff to it as we were working on it. So some benefits of a command-based workflow is, number one, it's very modular. So because command-based takes a very modular approach, you can break up your code into different sections, mostly commands and subsystems. So this makes it very, very reusable in other parts of your flow, right? So if you wanted to use your intake somewhere else, you wouldn't have to do any copy pasting. You can just call back the commands and the subsystems you've already initialized. The second advantage is similar to modularity, but it's very reusable. So from year to year or robot to robot, there's a lot of things that you can just transfer over without really worrying about if it's going to work or not. And because everything is sectioned up with the, you can write manage vendor libraries, and this is where you can add the additional libraries that we'll need. So up here again, manage vendor libraries, and then you'll do install new libraries using online method, and here you'll just paste in. You'll just paste in the JSON that you just copied. So you'll need to do this for more specific things that you start using. For example, if you're using a gyro, you might need to use this. You might need to install the vendor libraries for, let's say, your lamplight cameras. So as you start using more specific hardware, you'll need to install the specific features that come with it, and that'll be available on the vendor libraries. So once everything is set up, we're ready to start doing our coding. So on our left side here, we're able to see all our subfolders and files. So I'll open up the source, and then in the source, there should be the Java folder. And then this is further broken down into some files here that are just general files, like the robot container file, and two folders, which include our commands folder and our subsystems folder. So the first thing we'll do here today is set up a subsystem. So what you can do here is right-click on the subsystems, and it'll say create a new class or command. You can click on that, and then we're creating a subsystem. So I'll type in subsystem here, and it's going to ask us for the name of your subsystem. So we'll be working with the drive subsystem. So I'm just going to name it as drive subsystem, and it should be created for you. So right now it's just an empty place for us to start putting our code. But here you can already identify pretty much 3 sections. So anything above this this right here is where we can set up our initial libraries and whatnot we'll be using, like the classes. So the first thing we want to do is create the class for our motor controllers. So I am using the CAN Sparks. So the nice thing is, once you start typing, it will give you some suggestions. So I'm using the Spark Max. And the CAN here is just for identifying that it's on a CAN ID. If you are using PWM, you can also write PWM Spark Max, I believe. I'm not exactly sure. We only use CAN, but there is a feature that allows you to do PWM Spark Max. Yeah. So if you're using PWM, you can use this command instead, but we will be sticking to CAN for now. So the nice thing is, because we installed all the vendor libraries, as soon as I installed this, or as soon as I typed it, it automatically brought in this package here, which is the Rev Robotics package, and everything is installed for us. So after writing this, you're able to write the name of your first motor, and my first motor will be the left front motor. And then I'm able to create a new motor. And you'll see that it asks for 2 parameters. It asks for the ID number, and it asks for the type of motor. So for the first ID, it's just asking on what CAN ID your motor is. So this will depend on how it's wired and what you configure it to. But assuming that it's just 0, I'll just let that be as default. And then your Spark Max motor controllers can control either the brushed or the brushless. So here you can just type in your motor type. And we'll be using the brushless, so I'll just put in brushless. So that's all set up, and your left front motor has been initialized, and you're ready to use it. But because we have the 4 motors here, I'm just going to write this down a couple more times. So each CAN ID needs to be different, so just make sure you're typing in the correct CAN ID for your motors. So that's the left side, and we can do exactly the same for the right side. Okay, I'm just gonna copy this line down and just rename it to my right back motor and change the ID here. So what all of this does is that it lets us set up the motors, and now we have our 4 motors, and we've identified that they're all Spark motors. They're all motors that are using the Spark Max motor controller. So the next thing that I like to do is set up the encoders, because these motors have good encoders that we can use for our autonomous or just counting how many rotations it's done. So in order to do that, you're going to use a different class, and this one is going to be called the relative encoder. And you're able to name it whatever you want. I'll name it the right front encoder because it will be basing its values based off where the right motor is. So all you need to do is use the name of the right front motor and get encoded. So that's set up for us as well. And then we'll do the same with the left side. And this one will be basing its values off of the left front motor. So I'll just make sure I type in the correct motor name and get encoder. And then that's it. We're all set up there. So the next thing you want to do is set up a motor controller group. And what a group basically does is that it allows you to use one command to do both the right front motor and the right back motor. So that way you're not copying the same commands over and over again. And it makes it really easy for you to control each side. So the way you do that is you create another class, and this one is going to be the motor controller group. And you can see that all the libraries are getting installed here for me. And then you can call this whatever you want. So this one will be my left side. So I can call this the left controller group. The left motor controller group. And it's going to be a new motor controller group. And it's going to ask for 2 parameters, which is going to be your motors. So I'll put in the left front motor and the left back motor. And what this does is that it's basically saying the left controller group comprises of the left front motor and the left back motor. Whatever we do to the left side, we should also do to the right side. So I'll make one more controller group.
Sorry, question here. Is it only 2
sure.
parameters, or you can put 4?
I think you should be able to put more. I believe you should be able to put more than this. So however many motors you have on that side, you can put.
Okay.
Yeah, and yeah, just for everyone, if anything is unclear, just feel free to unmute and ask your questions. So yeah, I'll continue by doing the same thing on the right side. And then same thing here, new motor controller group. And then you can put in, so yeah, I think here it's allowing you to put multiple, so you can see in the parameters that here it's populating 4. So you should be able to put more than 2. But the example robot is just going to use the 2 motors. So the right front motor and the right back motor. So that's it. Now our motor controller groups are also set up. And the last thing we want to do is set up our differential drive. So this differential drive class gives us a lot of functionality because you can just tell it if you're using arcade or if you're using tank, and it gives you lots of control over each individual side. And all you need to do here is differential drive, and you can name it whatever you want. I just tend to call it differential drive. It's really easy to remember that way. And you're just going to create a new differential drive. And here you're going to pass in as the first parameter the left side. And as a second parameter, the right side. So these parameters are your controller groups that you just created. And that should be it for your initialization. So anything that you do inside here is only going to happen once. And this is a good place to initialize whatever settings you want to give to your hardware. So for example, the first thing you might want to do is as soon as your drive subsystem is called, you probably want to reset everything back to its factory settings. So what we'll do here is left motor front or left front motor, or restore defaults. And this is going to set it back to default settings. And I just copied that down 4 times. So here I can put a left back, right front, and right back motor. So this is just going to ensure that if I have any weird settings, it's just going to set it back to normal and everything should be working fine. So the next thing for our tank drive robot is that one side needs to be inverted because of the way the motor is mounted. If you give the same exact command to both sides, it's just going to spin in circles. So what you want to do is you want to just invert one of the sides, and it's usually easier to invert the right side. So here I can call.
Sorry, 1 second. So when you said restore factory default setting, so
Yep.
basically we have kind of tons of SparkMax setting. You can program using USB.
Yeah.
USB cable, right? So this reset will reset all of those settings.
No, I believe the settings should be exactly the same once you flash them in. But what this does is that if there's any like leftover encoder values from before or any like weird settings that have happened throughout your code because you've been running it should just set it back so it's in like its good state.
But the flash setting is still there. Just reset some dynamic setting. Okay.
No, that shouldn't be changed.
Okay.
So here. The next thing is we just want to invert one of the sides. So I'll invert the right motor controller group. And then all you need to do is just do set inverted. And this takes a Boolean. And because I want to invert the side, I'll just set it as true. And I want to make sure that the left side is staying in its default state. So I'll also just set that up. 1 second. And then I'll set inverted, and this one will be false because I want it to stay in its regular settings. So the last thing we'll do right over here is just reset our encoders. So if there's any leftover values that have been adding up, we can just set this to 0 so that our autonomous isn't doing anything weird. So here you're just going to set position and just set it to 0. So that way it's reset. And we'll do the same thing on the left front encoder and set that to 0. So now both our motor controllers are back to 0 and the encoders will start reading from 0, which is perfect. So in your periodic, you can run things over and over again. So something that's good to put in your periodic is just system prints. So in this section here, I can put any values that I want to be put onto my dashboard. So I'll put the right encoder and the left encoder here. So I can just keep track of them as I'm driving around and make sure that they're, like at about the same level because you don't want them to be, 1 second. Oh. One second. In order to do this, we just have to set up the function for it first. So just do that here. So below the periodic, you can set up functions that you can call in your command. So the first function we're going to do is a function that lets us read the encoder values. So because this is going to be returning a double value, a double is just a non-integer number, so any number with decimals in it. You can name it whatever you want, but good practice to name it something that makes sense to other people. So, and you can just return this. So whenever this function is called, this value should be sent to, it should be sent wherever it's being called. So now this function is set up and it lets us extract the left front encoder value. And we want to do the same thing for the right side. So I'm just going to copy it and modify it. So instead of left, just change it to right. And same thing here. Instead of left front encoder, this time we'll use the right front encoder, which is perfect. And then back in our periodic, now we can actually print it. So I'm just going to uncomment this line that I was writing before. And then smart dashboard put number will help us put a number and print it out to the smart dashboard. And here I'll print out the right front encoder value, which we're getting from this function. So once we do upload this code, the smart dashboard will print that out for us, and we'll do the same thing for our left side. And just change this to left. So the last couple of things we want to add to our subsystem is the way we actually control the motors. And we'll need three main functions here. The first one will be a set function, which just gives it a drive value and a turn value. And the second function will be a tank mode. So if you want to control your left and right side independently, which is usually a good thing to do when you want to drive or turn in autonomous without driver input. So you can add a tank mode, and we'll add a stop mode. So if for some reason we want to just tell our drivetrain to stop where it is and just brake in position, we can add a function for that as well. So this time I'll add a void function because I'm not returning any data. So I'm just going to call this function as set. And then here we're going to give it two parameters. My first is going to be a drive value, and my second is going to be a turn value. And I'm sure that when you've done your drivetrain before, you know that one side needs to be drive plus turn, and the other needs to be drive minus turn. So that way you're able to go straight and turn as well. So it's really easy to do inside of our differential drive the way we've set it up. So all you need to do is call that differential drive. And there's an arcade mode already that's created within it. And here you're just going to pass in the drive parameter and the turn parameter. And WPI Lib and Visual Studio Code will take care of all the addition and subtraction of drive and turn. So this will get your drivetrain running in arcade mode. All we need to do is pass these parameters, which we'll do from our command. Okay, so we'll add another.
Sorry. One quick question here.
Yep.
So when we do differential, for example, when we do the turn, and then it's related to the encoder value versus the wheel size, right? How much turn, how much you turn around. How does those information pass to the class?
Okay, so the turn information is not coming from the encoder. This is coming from the joystick. So I'm sure that in the normal way we do things, you would probably do it like left motor equals to your drive value, which is coming out from your joystick, plus your turn value. And then on your right side, you would do something like right motor equals drive minus turn for arcade.
Okay.
But this differential drive, it basically takes care of all that for us, so we don't need any of this. But if you weren't using differential drive, you do it like this. And these values are coming from your joystick.
Okay.
Cool. Yep. So I'll come back here and add my second function. And this one will be my tank mode function. And for tank mode, you need a parameter that will control the left and the right independently. So I'll add a left and I'll add a double right. So here, basically, I can just send it a speed. So I can send it something like left should operate at 100% and right should operate at 80% to get like a nice turn. Or I can set it something like the left side should be driving forward at 50% and the right side should be driving backwards at 50%. Whatever you need it to, you can do it from here. And because we are using differential drive, we can add that built-in functionality using the tank drive command, and it will take care of all that for us. The last thing we'll do is add a stopping function in case we want to emergency stop our drivetrain. I'll just call it stop. This doesn't need any parameters because to stop the motor, it just has to be at 0 power, and it should stop driving with any input power anyways. So here I'll just type in differential drive dot stop motor, and this will take care of stopping everything for us. So basically, if I were to go over this again, everything here is set up for us now inside of our subsystem. So we should be ready for our command coding. But to go over this again, in this section before the drive system, the drive subsystem, you're just basically initializing all the hardware you'll be using and just creating some command groups. So you can have some motors, which we've done here. We have our encoders, which we've done here, and our control groups. And finally, everything feeds into our differential drive. And it allows us to use the built-in commands, which is really nice. Inside this section, we put in everything that we want to be only run one time. For example, resetting your encoder values. You don't want this to be running over and over again because if it's setting to 0 over and over again, it won't actually count the distance. So whatever you need to do only once, you can do inside this section. So everything after that is running over and over again every cycle. So we can print stuff in the periodic and create some custom functions, which we'll call in different sections of our code. So from our command, we can call the set function or the stop method, and it would basically control the hardware how we've programmed it over here. So that basically means our entire subsystem is set up, and it's perfect for just the drivetrain. There's a lot more that you can do with it. For example, here you can add a gyro, or you can add other sensors. You can add some like odometry. There's a lot of different things you can do. But from a beginner standpoint, this is everything that you need to get started. So we're good for our first subsystem, and then now we'll learn how to make our first command for the subsystem. So instead of the subsystems folder, I'll go to the command folder and do the same thing. You can click right click and do create a new class or command. And then here, because we're creating a new command, I'll type in command. And then here you can just put the name of your command. So what we're creating here is the default drive command. So the default drive command will be happening as long as no other commands are taking priority. So I'm just going to call it the default drive command. And the default drive command is just you operating your drivetrain using the joysticks. So it's created for us, and similar to the subsystem, it's created a nice template for us, but it's a bit different as well. So the way this one works is that it has a couple of different sections to it, and the comments kind of explain what these are for. So up here, you're actually creating and initializing everything. In this one, this initialize method here, that's only going to run one time. So if you wanted to, for example, reset your PID or reset some values for the command, you can easily do them from the initialize. The execute happens over and over again. We'll jump to the is finished here. The is finished is basically telling us, should the command be on or should it be off? So here, if I were to change this to true, the command would pretty much end instantly, and it would stop running. But I'll keep it at false because we always want this command to be unfinished, and we always want to be able to drive our drivetrain without any interruptions. But then if this section is true, this function will basically kill the command. It would say, okay, this command is finished, time to move on to the next one. So the reason this section is really important is if you're doing something beyond just driving the robot. For example, on our robot, we have a function where you can just press a button and then it will drive a certain distance and then it'll stop. So what I would do here is basically say, once you get in the range, so within like 30 centimeters, then you can change this to true, and then you can move on to the next command. Otherwise, leave it to false. So for now, you don't have to worry about it, but is finished is also a really important part you'll use once you start doing more advanced stuff. So we'll start setting up our actual subsystem here. Sorry, our actual command here. And the first setup we'll do will happen above this section right here. So here's where we'll set up our subsystem, and here's where we'll set up our joystick. So here's where we can call the drive subsystem, which we just created. So it was called drive subsystem, and you can see that it's already pulled it into our file. And here you can name it whatever you want. The naming convention I tend to stick with is everything capital. Just like that. And then we'll do the same thing for our joystick. So we'll create another class for that. And then I just tend to keep this as joystick. But you can name it to something else if you wanted. Like joy would be fine. Controller would be fine. Whatever works for you. But I'll leave it at joystick. And then in here, the first thing we want to do is pass in the parameters that will be sent from our robot container file. So what I'll do in this section is just pass in the things that this command needs. So what this command needs is it actually needs the subsystem to send the commands to. So here I can do drive subsystem. And I'll name it something different. I'm just going to call it drive. And then we also need the joystick, which is going to be passed through our robot container. And I'll call this joy. So the next thing you want to do is you want to make sure that there aren't multiple instances of drive subsystem running, because that'll cause lots of interruptions. So all you have to do is just do this dot drive subsystem equals to the drive subsystem that's passed in over here. You'll do the same thing for any parameter that's passed through here. And I'll do the same thing for the joystick. So this dot, the joystick class that I've created here, is equal the joystick class that's passed through my parameters. The last thing you want to do in this section is pretty much add requirements. So what this is saying, that in order to run this command, it needs to have the drive subsystem. So if any other command is using drive subsystem, it's going to stop that command to make sure that only this command is using drive subsystem. This is an essential step, because if you don't put this, there's a chance that multiple different commands will use one subsystem at the same time, and this will cause for unpredictable behavior. So this line here is a must. So the next thing I'll do is I'll just create some variables up here, and I'll call them drive and turn. And you'll see in a moment that these are for our joystick values. And then in the initialize, I'm just going to set this to 0. And the reason is we don't want our robot driving off unless we've actually given it any commands. So you just want to set it to 0 as a safety. And then what we'll do in this section here is we'll get the values for we'll get the values that need to be sent to the motor from the joystick. So what this is going to equal to is just the joystick class that we just created, and then the function we're going to use is get raw axis, and that's going to get us the value from +1 to -1. So if you were to put your joystick all the way down, our value would be -1. If you put it all the way up, it should be +1, and then you have a number in between when you're not fully up or down. And then it's asking for the axis. So the controller we use for our robot is the Logitech gamepad controller. So we use the left up and down axis to control our drive, and this axis happens to be 1. You may choose to use a different axis. So whatever axis you're using, just double check with the controller, and then it should work. And also the hardware I'm using here is the Logitech. You might be using a different controller for your robot, probably an Xbox controller. The logic is going to remain exactly the same, but the way you write it might be slightly different. But the logic will remain the same. And the last thing we'll do is the same thing we'll do except for turn. So here I'll add a joystick, get raw axis, and then this axis, the one we use on our robot, is on the right side, and it's the side-to-side axis. So the number for this one happens to be 4. And that's it. So now all you need to do is drive subsystem. And if you remember, in our subsystem here, we created the set command, which takes in your drive value and your turn value. So here we're able to actually pass those values in. And then you can just do drive and turn. So on our robot, when I uploaded this code, it was driving backwards. It wasn't driving forward, and it was just opposite. So in my case, I'll just change this to negative. On your robot, if it's driving correctly, you can leave it as is. If it's driving backwards, just set it to negative. So that should be it for this command. This is a super simple command. And to go over it again, all we're doing is just initializing some variables that we'll be using and the classes we'll be using. So the subsystem and the joystick class. Here, we're just making sure that we're only using one instance of each class. And we're just making sure that we're adding the requirement so that no other command can use that subsystem while this command is using it. Inside initialize, I'm just setting everything to 0 so that nothing unexpected is happening as soon as the command starts. And finally, in execute, I'm just mapping the drive values and the turn values, which I'm pulling from the joystick and its specific axis. And then using the set command we created for the subsystem, I'm just passing those along. So that's pretty much it for your subsystem and the command. Does anybody have any questions yet? Or anything about what I did so far? Okay, I think we're good then. So the last step is just to do the robot container.
Question for you.
Yep.
In that robot subsystem, how would you implement the encoders on that system so that it drives straight or in a PID loop, correct?
Yeah, great question. So here, all it's doing is just getting the values for me. So the way I've been doing it is inside here, you can actually pull the values. So I can say something like left. One second. I can just say the left encoder is equal to the drive subsystem dot get or left encoder value. Okay, right here. So I'll do that. I'll get the left encoder value. I'll get the right encoder value. And then now I have the left and the right sides, and I would print them out and see what they're reporting. And then the way I've gotten our robot to drive straight is using the gyro as well. So you can set up similar to how we set up the encoders here back in your subsystem. You can also set up the gyro, and then you can send the yaw values to your command. So using here, you'd have to add the navx gyro, and then you can send those values over to your command. And then now using a combination of my encoder values and my gyro values, what I could basically say that is if the left encoder value is reading smaller than the right side, it probably means that it's starting turning a little bit. So add a little bit of value using PID to the left side until it doesn't balance out. So now if the left side is reading higher than the right side, I'll use the same thing using my gyro and my encoder values. I'll add some more power to the right side until the gyro doesn't center out. So using that in like a calibrated PID loop should get your robot driving pretty straight, even if you were to like kick it or if it were to bump into something. I hope that was clear. If not, I can explain that again. Okay, so I think we should be good for this side. I'll delete all of that. And then the last thing we want to do is go into our robot container. And then in the beginning, I kind of explained how this is the place that ties everything together. So your robot container is where your commands and your subsystems will interact with each other. So this template is nice to give us this example here. And using the way they formatted it, we'll create our own subsystem in here. I'm just going to use the same format they've done. And then their naming convention here is m_example subsystem. You could use that same formatting, or you can just call it drive subsystem. It's really up to you what you want to do. So, but because they stick with the m_, I'll stick with that too. But it's really up to you what you call it. And then here you'll just call in that subsystem that we called. And then this will be the place where we actually make changes to the subsystem. And we want to make sure that there's not multiple instances, which is why we did the this dot drive subsystem equals drive subsystem in our command. So this is the official place where we'll control it from. So once that's set up, the next thing we'll do is set up our joystick. So once again, we'll use a joystick class, and you can name it whatever you want. I'll just call it joystick, and it'll be new joystick and the port number. So some teams stick with one controller, some teams stick with two. So port 0 is for your primary. If you want to create a secondary, you can just add a new joystick and call it your secondary. You just have to change the port number. For now, we're good with one joystick. So I'll remove this. So when I say joystick, I mean one controller. So that's all set up for us. And then now we can jump into this robot container section. And then here you can see that it's already given us a command called configure bindings. So what configure bindings does is that it binds joystick and controller values to commands. But because this will only happen if you click a button, because that's when it gets triggered. But we want something that's always running in the background. And we want our joystick values to always be checked and always be sent to our default command. So what we want to do here is add a default, and we'll make a new function, and we'll just call it default commands. And the default commands will be constantly running in the background. So anything that needs to be constantly updated, this is where you would do it. So an example of some things that you might run from here are commands for your drivetrain, commands for LEDs if you have them always performing something. For example, in this year's robot, what we did is that we were constantly checking the sensor inside the intake. If it was active, it would be green. Otherwise, it would always be checking and it would be purple. So basically, things that you don't want to be controlled from buttons, you'd put inside the default commands function. So here I'll create my default commands function. And here's where I can add the command, the default command, to the drive subsystem. So in my drive subsystem, I'm going to add a default command. That set default command is what we're searching for. And then inside here, we'll give it the command name that it's looking for. And in our case, we created just one command, which was the default drive command, which is what we'll pass here. And then obviously we need to give it the two parameters, which is the drive subsystem and the joystick. So that's pretty much all you have to do in order to get your drivetrain running in command-based. All of this stuff is for autos. So for just from a teleop perspective, this is pretty much all we need. And now we've successfully paired up our robot container, our subsystems, and our commands all together. And once we upload, it should work on our robot and get it driving. So I'm going to stop showing the code and I'll jump back into my presentation here. So we did the walkthrough in case I wasn't clear about what hardware I was using. So this was based off the Logitech controllers, the Neo motors, the SparkMax motor controllers, and it's written for a basic tank drive robot. So if it's not going to work on a swerve, it's just going to work on your regular tank drive. And it's a good exercise to get started and understand how the different classes and files interact with each other. And the thing you'll notice in your own programming is once you get one simple subsystem working, it's really easy to just add on from there because the logic remains pretty much the same. So if you wanted to add an intake or some other type of mechanism, it'd be a very similar approach. So if your hardware is different, your logic will stay the same, but the libraries you use might be slightly different. So for example, if you're using the Falcon motors instead, you just need to use their libraries and their specific commands rather than Rev stuff. So that's just a slight difference. But to just touch up on some additional resources you might want to look into once you're trying to continue on with this is best resource is definitely the FRC WPI lib documentation. So for brand new teams, they have the Zero to Robot series, which kind of just takes you to all the steps from building a robot to preparing it and coding it. So if we look at this section right here, they have a create your test drivetrain program. I think this one's in lab view, but it should be a Java version. Yep, 1 second. Right here. So this is basically doing pretty much the same thing we did. So creating a new project, setting it up, and creating the project, writing some code for it. I think they did this one in time-based, but it's still a good resource to start looking. And then they have this entire programming basics thing. So like CAN devices or hardware APIs. Then so they also have the advanced programming section. So if you're ready to start implementing things like vision or command-based, they have a whole section on that as well. So this is a great place to start advancing once you've got the drivetrain up and running. The next best source that I personally found is I found a really good YouTube channel, which is called Zero to Autonomous. And it's a team called Helix, I believe. And it's a 6-part series, which takes you through just setting up your code to time-based to command-based. And I believe they also have a section for Swerve Drive. So if you are a Swerve Drive team, you could look at that as well. And another good resource that I found useful is looking at other people's GitHub files. So here I linked mine. So CNE project is just something we were working in the off season. So this is something I work on regularly, and then it just has some of the cool stuff we've been doing. So like you can add a file where all your constants stay so that your code is nice, or just adding in more subsystems. So you can see that we have a couple extra subsystems here, or commands and autonomous routines. So we have more stuff here. This is our team's GitHub. You can access this if you want to. It's all online. Or I would also recommend looking at some of the bigger teams that do exist out there. And my recommendation would be something like Spectrum Robotics, because they do put a lot of the code for other teams to see. So that's definitely a really good learning resource. And there are other sources out there on GitHub, like the Toronto Coding Collective, which has a couple Toronto-based teams that do put their code up there. So definitely looking at other teams and what they're doing is a good way to learn. But yeah, other than that, that's pretty much all you need to do to set up your command-based coding. I've also put my email up here, so if anybody has specific questions, either now or throughout the season, I'll try my best to get back to you. But does anybody have any questions they would like to ask me before I kind of stop sharing my screen here?
Yeah, what is the YouTube channel again?
Yeah, sure.
Zero to Robot.
I'll put that link up for, I'll put it in the chat as well. One second, let me see if I can open it up here.
Have a snack.
Advertisements.
You excited to see your flavor?
But yeah, okay, and I'll just put this in the chat for everyone to see. But yeah, this is a really good source that I would use if you're starting off with just command-based coding.
Okay, Nihar, thank you for all the information. It's really useful, and I have a few questions, but not maybe not from the basic coding. The first is you keep mentioning gyro versus the encoder, and since we have encoder, we can tell how much wheel has run left side or right side, right? Is pretty accurate. So
yep.
Why do we still need a gyro?
Okay, the reason I like to use gyro is because when there's like a big change in movement, it really does help with that, because the encoders, they can't tell angle, right? But the gyro is able to do that. So for example, if you wanted your robot to travel straight, but somebody kicked it from the side, your wheel isn't going to turn that much, but your angle might be way off.
Okay.
Because your angle is way off, you want the gyro to be able to correct you back into a straight position, and then you can start measuring your encoders again. So if that
okay, so you basically use first you use a gyro to recalibrate the wheel position.
Yeah.
And how much we can trust the gyro? How much error it could introduce?
So the gyro, in my experience, has been pretty accurate. The one we've been using on our team is the NavX. So, for example, to climb on the docking station this year, that's what we based our entire code off of, and it worked 100% of the time, which is why I'm pretty confident that this gyro is really good. But that's where the entire idea of pairing up the gyro with the encoder comes in, because now you have two systems that are working together, and they can kind of accommodate for each other's weaknesses. So the weakness of the gyro being it might not be as accurate, and the weakness of the encoders being that they can't track big changes as quickly. So using them together will kind of give you a more accurate solution.
Okay, thank you. The next question is, have you guys ever experienced any like a neo motor broken due to the internal magnetic fallout? If you're driving too hard and then the internal magnetic fall off?
Not that. We did have one issue with our Neo where I think we put the screw in too much and it damaged the insides. But to answer your question specifically, there are methods in the Rev client and through the code where you can limit how much current is going through. So if you notice that it's going beyond 80, for example, you can set it up so that it doesn't pull more than that.
Oh, okay. Another challenge we're running into the PID control. So yep. when we set the PID position, for example, so the motor is always driving like crazy in the beginning because of the difference are too much, and driving crazily, and that's causing the motor was overdriven in the beginning, and then once it's getting close, it try to suddenly stop. So we're trying to multiple way how to slow it down in the beginning. Is there a way that in the PID actually can do that?
Yeah, there is. So that's an error that I was running into before as well. And that's probably because your PID is mostly based on just the P value. You're going to want to reduce the P value and mess around with the I and the D value as well.
Okay.
So you're going to just want to mess around. So reduce your P for sure and mess around with the I and the D, and you should get smoother results.
Okay. So you're saying that tuning up the PID, so we should be able to doing like a slow start.
Yeah, exactly. So it's all just going to be tuning. The more you tune it, the smoother your control is going to be. So just spend some time. What works for me is very trial and error. I know you can do this using math and like MATLAB and stuff as well. But what's worked for me is I'd sit down with a table of different values, and then I do P, I, D. So I'd put the three values. And then, for example, if I start with a P value of just 1, and then your I and your D are 0, you can kind of record what's happening. You can see what's happening on your observations, and then try reducing your P value or try increasing your P value. until it gets pretty close. So once your p-value is pretty close, you can start implementing the I and the D. So sit down with the table and just go through what values are working, what isn't working.
Okay. Okay. Great. Thank you.
I'm gonna paste my email. I'll share my email in the chat as well. I'll stop sharing. But yeah, my email is right here in the chat. That should have, like, if you have any specific questions, I will do my best to answer them. But also, just to be perfectly honest, I only started doing coding for FRC December-ish, December, January-ish, and only did command base since March. So there's still a lot that I'm learning, but I'll help you if it's something that I know.
Oh, you're surprisingly good in short term.
Thank you, thank you. I've had a lot of support from my team, so.
Okay.
Yeah. Anybody have any other questions?
Yeah, I have a question. Do you know where can I find the best YouTube channels? Like you already mentioned YouTube channels, right? But do you know any network sites that I can find, like to Java practice and stuff? Like how can I learn Java from any, network sites and stuff, internet sites?
So have you tried Java from scratch from like do you know a bit of Java or are you just starting out?
I'm just starting to Java, but like I have some coding experience, but like not on Java.
Okay.
So I just started Java and I wanna know how can I learn from internet,
So yeah, firstly, you're probably just gonna want to learn the basics of Java and the syntax and stuff. So there should be a couple good crash courses on that on YouTube. I think Code Academy is one of them. Free Code Camp is another one. Here, let me see if I can find something specific for you. Just give me 1 second. There's lots of like big videos, like 11-hour videos. I personally haven't watched any. Try maybe starting out with a smaller one that's like an hour or something. I just found this one. Research. Yeah, and then William put another really good one, which is Free Code Camp. They're a great
Step
place to
into
start. So the way this works is the code that they're using might be for a different purpose. Like for example, they might be using it for apps or something. But you want to use it for robots. So don't go too deep into it, but just definitely learn the basics of how the things are working together. Anybody have any other specific questions?
So thank you very much, Nihar. It was so great to have you present for us this evening, and most appreciated. Quite a thorough introduction. And even though many of our audience are now just starting out, I think this will prove to be a really valuable resource, as they'll be able to refer back to it as they get their robots going. And if anyone else has questions or suggestions for future topics, please feel free to email or message. And I'm sure Nihar will be able to share with us his slideshow, maybe a link to his code. That would be really great. There have been a few requests for that. Members of our FRC community throughout Ontario, it's been a really great time having you here on the call this evening, and really look forward to seeing many of you very soon at the Southwest International next weekend and the following weekend in Hamilton, and at various other events such as the SWAT-posium coming up on December 2nd. And hope everyone has a wonderful evening. Thank you again, Nihar.
Thank you.
Thank you, William. Render the meeting. Thank you, Nihar.
Thank you so much. I see, Randall, you have a question?
Yeah, I do, William. It's something for you and me to discuss after everybody leaves. If I
Okay.
could just a couple of
I
minutes.
do have 2 other meetings right immediately. Do you think I could call you in the morning? I already have people who are physically here at my house for meetings. Is it okay if I call you in the morning?
Sure.
Okay. I'm sorry about that.
Absolutely.
I have 2 meetings. One. So most appreciated, and I'll give you a call very soon in the morning.
Okay, thanks, William.
Thank you.